number of chapters is not consistent with our progress. We skipped chapter 3. This is the arrangement in chapters which relate to topics that I generally follow when I teach a complete course on remote sensing. In this case, we don't have so much time at our disposal, and especially you're not interested in all these topics. So I'm skipping some of them. Chapter 2 and chapter 3, for example, are related with possible platforms that can be used for Earth observation, and two types of data, to platforms that may be used, and to technologies that can be used, which you may not be interested in. So we skip them to move to remotely sensed data. And we pick up again the scheme that I showed you in the first lecture, where we discussed the physical phenomena that are involved in remote sensing to understand, to go deeper into the meaning of the data that you collect through the instrument. Now, we move basically at the interface between the physical world and the data world to understand a little bit better how these physical quantities, these physical variables are turned into numbers. This process may take different forms. I will focus mostly on how hyperspectral data, multispectral data is translated into data, because it's somehow the easiest one to be taught, especially in a short time. And then we will move on to looking at the properties of these data and how we can characterize them. So basically, whereas the previous focus was on the physical phenomena, now we're moving the focus to data themselves. Okay. So we discussed previously that we are interested in the reflected radiation because we know that the information that we're interested in is somehow hidden in that wave, and we need to sense that wave and turn it into numbers that we can then process through an algorithm using suitable means. So before we can access the information, we need to be able to read the raw data. How do we generate this raw data? And especially in multispectral remote sensing, but hyperspectral works on a similar concept, we need to basically break down the incoming radiation by wavelength. Remember, in the graphs that we saw in this morning's lecture, they were characterized by a shared characteristic, which is the fact that on the horizontal axis we had the wavelength. Okay, why? Because the wavelength, different wavelengths relate to different behaviors, and we need to break down the behavior of the target into all the different wavelengths that are being observed in order to make sense of it. So there's a formal definition of what you are measuring in physics, in physical terms. I won't go into the details of the formula. What we're measuring here is basically a power divided by an area, divided by a solid angle, and with an adjustment factor which relates to the angle under which such power is acquired. Okay, so there are physics consideration behind this formula, but the basic concept is that when you do remote sensing in the optical domain, radar domain works a little bit differently, but the underlying concept is somehow similar. The idea is that you're measuring a power coming from a definite direction. Okay, so when you do remote sensing, you're measuring power coming from a specific direction over a specific solid angle. And then if you take the next step, the idea is, okay, I'm measuring on a certain direction over a certain solid angle because I am interested in what happens on the projection of that solid angle on the Earth's surface. Does that make sense to you? I'm measuring there because I am interested in what happens exactly there. Hence the angle, hence the direction, hence the solid angle. Okay. Then, further step is I don't do that just for one place, one solid angle. What I do is, technically, is I iterate that process for multiple locations, and I actually acquire an array of measurement, not just one. Okay, I don't set up a satellite system to observe just one location. The good of the satellite system is that it flies above the globe in multiple locations. So it's best if you can make the most out of this big expense, which is putting a satellite up in orbit. So what actually happens is when you fly a satellite, you do this, you measure this variable in multiple directions, possibly at the same time, and you collect all this data and you send it to the ground station, okay? But physically, this is what we are talking about. This is one measurement, okay? So that's about the geometry, but when you think of breaking down into wavelength, the concept is you not only measure the power from a given direction, you also break it down by wavelength. So what you take is, for those of you who may be familiar, who have a signal processing background, they may find it convenient to think of it as a Fourier transform of the incoming wave. I'm decomposing the incoming radiation into its spectral components, okay? And in some sense, I'm filtering then these components by using certain frequency slots, which I call bands, okay? If you don't have a signal processing background, then you can still think of taking the horizontal axis with all its ideally continuous series of measurements, and taking averages on chunks of that axis, of that horizontal independent variable. Okay, and these measurements, these individual contributions from each portion of the horizontal axis are called bands. Okay, and this concept has a technological counterpart. So when you decide what are your bands, when you decide what are the pieces of the spectrum that you're going to measure, that reflects into the hardware of the sensing device, okay? So are you still with me? Okay, great. So it's a design choice. When you're designing a sensor to be placed on board a satellite, you're deciding this. You're deciding how to break down the observed radiation into bands. And it is something that is not easily changeable. Some devices have some flexibility in that they can be programmed to move the bands a little bit. But generally speaking, once you have designed the sensor, then you have also frozen the bands. So you have frozen the distribution of wavelengths that you're measuring independently. Okay. technically, you may remember from your physics lectures at the elementary or intermediate schools even. So this is something which is presented at all levels of school. Okay, you take the sunlight and you pour it into a dispersing element, and then you get the different colors. What are these different colors? What do these different colors represent? Different wavelengths, right? So basically, what you see here is just the illustration of this concept. What you do is you take the incoming radiation, which is all in one place, and then you break it down into its spectral components, and you measure them separately. Now, where you decide to start and end each measurement, which will average over that interval the power, then you're deciding what bands you are interested in. This is where you have the distinction that I discussed with some of you from between multispectral and hyperspectral remote sensing. Okay, let me open this parenthesis here. You can decide that you take large chunks of these spectral intervals, and that's called multispectral remote sensing. Or you can move on to the next step, which is take very small intervals, and so that you can represent the reflectance curve more accurately, and that's called hyperspectral remote sensing. Okay, and from a technological standpoint, that's very different. So much so that multispectral data is widely available. Hyperspectral data is not that common for space-based systems because it's technologically very difficult to achieve decent hyperspectral measurements, okay? Because you're working with very weak signals, it's very weak, and you're still breaking it down into pieces which are even weaker, and there's a number of technological reasons why it's not easy to do. But it's feasible, and it is operationally done. So one concluding remark, this is conceptual, but it's not only conceptual. If you were to take a satellite, a multispectral satellite, open it up and look inside, you would find something like that. Okay, nice to know. Yeah, so if you look into a single component, like if you were to say, okay, now the horizontal axis has become vertical to fit it into the previous scheme, but what happens if we take a single component? Well, we're basically taking a wave, which is the object we started with. What can we measure of that wave? As a sine wave, we know we have a wavelength. We selected it because we wanted to look into this. But we can also measure the so-called phase with respect to a certain reference, how shifted is that wave. But we can also measure the so-called polarization of that wave, which is what's the direction of the electrical field. Remember, we started from the concept of wave, which is electrical and magnetic field traveling together, et cetera, et cetera. So the electric field is always perpendicular to the propagation direction, but nonetheless, we can look in different directions, which are all perpendicular to the propagation direction. That's a concept of polarization, okay? That's also measured in remote sensing systems. And so when we carry out a remote sensing operation, we are observing a certain area, we're focusing on a certain wave coming in, we can decide to measure the amplitude, the phase, and/or the phase and/or polarization. Now, we will see that in the case of optical remote sensing, it doesn't make any sense to measure phase and polarization because these are basically random for some physical reason, which I not explain here. It would take too long. But in the case of optical data, what you're measuring is just how strong the radiation is, which is coming into the instrument. Okay, so essentially, when you work with optical remote sensing, you're working with power measurements. And you do not distinguish phase or polarization because it doesn't make sense to do so. It doesn't add any useful information. When you move from the optical window to the radar window, then things change quite a lot. And measuring phase and measuring polarization starts to make sense. Okay, but we'll discuss that at a later stage. Now, as I said, talking about data, this is what happens conceptually for one single measurement. But as I said, you're not interested in a single measurement broken down into bands. This is useful, but it's not all. Since you can look at a particular direction, why can't you look at many different directions? So you fly the satellite, and then you design the device in such a way that it can either scan, okay, so move from one location to the other as the satellite flies, or even look at them all at the same time if you have more than one sensitive element, which is the most common solution. So you fly the satellite and you activate all these sensors all in a row, and each one of them will read on a particular location. Basically, it's like as if you were pushing a broom, scanning the Earth's surface on a broad area, okay? Generating a so-called swath or satellite swath. Multiple measurements done at the same time. Then, just to reconnect with the beginning, if you take some of these measurements, you crop this swath, and you get a chunk of data, then you can turn that into an image, which again, it's not a picture. It's not something that someone has pushed a button and it generated an image. It was acquired continuously, and then some organization strategy will define where it starts and where it ends, and then when something ends and the next one starts, et cetera, et cetera. But it's not a picture. Okay, so what can we expect in terms of arrangement of the data? Well, most commonly what happens is we have a structure like this where the spatial scanning that we have set up, so the motion of the satellite together with the fact that you're acquiring on a line, basically, will produce two spatial dimensions. One is generally the advancement of the satellite, and the other one is across the path. So you have these two spatial dimensions, which you should be aware they do not generally match the geographic direction, the main geographic directions. So this is not north-south, this is not east-west. Why? Because generally the orbits of the satellite are tilted with respect to the cardinal directions. So satellites almost never fly north to south, or let alone east to west. They generally fly with something like 8, 10, 12 degrees with respect to the polar axis, okay? So these are spatial directions, but not cardinal directions. And then there's a third dimension, which is basically the spectral dimension. Why? Because these are the bands. Okay, so for every possible location, you break down the signal into spectral components, and these spectral components are separate measurements, in fact. Okay, so every time you fly a satellite and the satellite is in operation, you're basically generating a 3D structure of data. 3D structure because two of the dimensions are spatial. They relate to the specific location where you're doing a certain acquisition. And the third dimension relates with the spectral characteristic. So now the question is to see if we are still on the same page. If I were to build a reflectance curve, where should I look to? So which of these directions would serve my purpose of building a reflectance curve? Sorry? The K direction, right. So basically, what you have here in the K direction is a summary, is a sampling, actually, of the spectral reflectance of the object that happened to be there. Okay? So there was something there. That something reflected the radiation which was broken down and measured in all its spectral components. And again, your design choices that you made when designing the instrument will determine what these bands mean. Okay. So this is the basic concept of how data are arranged. But the way this data is collected and generated determines some important features for these data. Namely, one of the most important things that we should know about the data is its resolution. I think more or less all of you have a concept of resolution, so I don't need to repeat. Is there anyone for which this is not clear? What is resolution in physics? I don't get a definite feedback from you. So are you aware of resolution? I imagine that. What is the level, the minimum difference that you can, what is the minimum difference in the measured variable that produces a perceptible change in your measurement? That's resolution. Okay, so resolution is generally explained in physics in terms of, for example, resolution on distance, on a distance measurement. What is the resolution of this ruler here? Well, the smallest difference I can see is that of 1 millimeter. So the resolution of this measurement device is 1 millimeter. Okay, something similar can be thought of for remotely sensed data, except when you are doing remote sensing, you're involving a number of variables, not just one. Let me explain a little bit better. When you work with remotely sensed data, you don't just have to do with the power measurement. That's a factor for sure, but you're also working with not just different powers, but different wavelengths, different locations, and different times, besides, naturally, different levels of incoming power. So correspondingly, you have different levels, different concepts of resolution for remote sensing. So one very important is spectral resolution. I already mentioned that. Depending on how fine are the intervals that you define when you decide how to break down the incoming radiation, that defines a resolution. Because the smaller the interval, the smaller the change in the curves, in the reflectance curve that I can perceive using that sampling of data. Okay, and that's where, as I said, the difference between multispectral and hyperspectral lies. Sorry. Yeah. So the same object may be observed at a handful of wavelength in multispectral, or on a very fine series of individual samples, which will help me defining or drawing almost complete reflectance curve. Okay. What is the practical difference? What is the practical difference? Well, on the one side, I already mentioned this type of data is much more widely available than this. But on the other side, this type of data will never be capable of describing the observed object as well as thoroughly as this type of data can do. Okay, so to stick to the example of vegetation, multispectral data can let you identify vegetation for sure. But for example, if you are interested in distinguishing various species at the same time with one single acquisition, then you will need hyperspectral data. Okay. Another practical difference is that this is big. Okay. So if a typical multispectral satellite acquisition takes on the order of hundreds of megabytes, okay, this is a very low-level discussion, but it's something that you need to take into account when you work with this data. The typical multispectral, for example, Sentinel-2 multispectral data set takes up on the order of 600, 800 megabytes for one acquisition. When you move to hyperspectral, like for example, Prisma, we're talking about 3 to 5 gigabytes for one acquisition. Okay, this is one more confirmation, if you wish, of the fact that you're not having to do with pictures. What is the typical size of a picture? When you say a JPG file on your computer, how much does it take up? Hundreds of kilobytes, maybe a couple of megabytes, not 800 megabytes. Okay, so not a picture, definitely. Okay, then another important concept is spatial resolution. This is the most popular way of meaning resolution. So when you think of resolution, like for example, even in the smartphone camera, resolution is defined as, arguably defined as megapixel, how many megapixels. Because more megapixels means smaller pixels, so better definition, et cetera, et cetera. In this case, this is similar, okay? I won't go into a deep discussion because we don't have time, but basically, satellite, Earth-observing satellite may have different levels of resolution. So the pixel, the individual measurement unit may be bigger or smaller when projected on the Earth's surface, and accordingly, you may be able to see smaller details, or you may be missing them. Okay, so technically speaking, it's very difficult to increase the spatial resolution. Okay, so 1 meter data doesn't come for free. 0.5 meter, it's even worse. 0.2 meters, which is more or less the current level of resolution, the cutting edge of spatial resolution for civilian applications, at an even higher price, technologically speaking. You may be tempted to think that resolution, higher spatial resolution, is always better, because if you can see finer details, you can see better the object that you're interested in. But you should be aware of an important fact in terms of, well, a number of important facts. When you have to do with higher resolution data, then generally it costs more. But let alone the price, it's not always available. Don't think that whenever you need an acquisition on a certain area, a satellite is there to serve you. Okay, so data may be there or it may be not there. And especially if you want to go for very high resolution data, then very frequently it's not there at the time you need it. Smaller areas, if you have a high resolution, then you do not, you cannot cover a very broad area. Also because the amount of data that you need becomes prohibitively giant, little heritage. You can't go far back in the past because as the technology evolves, you get higher and higher spatial resolution. But in the past, for heritage data, you can get very high resolution. And while, well, this is more difficult. So let me focus on this. I show you a number of reasons why, of individual reasons why very high resolution data is not always desirable. What I'm showing you here is that it's in fact not that desired, okay? So starting from the concept that, I mean, if you think of it as a picture, having a smartphone with 20 megapixels is better than having a smartphone with 3 megapixels, okay? But we're talking about very different things here, okay? Again, we're talking about measurement. I may not be interested in very detailed measurements. And in fact, if you look at these graphs, which represent as time went by since 1972, when the Landsat series, which was the first mass producer of remotely sensed data, entered into operation. Okay, so this is basically the oldest sort of systematic archiving of data. You can go back as far as 1972, but not further. Starting from these times and moving up to, well, almost present day, we have on the vertical axis the so-called spatial resolution for panchromatic data, which means the systems that give up spatial resolution. They just focus on measuring the overall incoming power with the highest possible spatial resolution. Okay, so this is the record man of spatial resolution. And you see that as time goes by, the average resolution of the existing system goes down. Okay, naturally, we're talking about the champion of spatial resolution, panchromatic systems. But if you think of general purpose systems, so multispectral, where spectral measurement are actually retained, you will notice that the technology lets you actually move down in terms of spatial resolution, in terms of size of the pixel, but actually so many systems still offer, see, these have been, the coarser resolution options have disappeared here, but they are still there in this case. So people are still interested in gathering information at a coarser spatial resolution. Why is that? Why is that? I mean, if you can have better data, why would you go for worse data? Sorry? Yes, for a number of reasons, because it's not necessarily worse. When you switch to, when you use low resolution data, you may have better coverage, especially if you're observing global phenomena like factors involved in climate change or carbon cycle or whatever else you can mention in terms of environmental monitoring. This type of data is more relevant than that. Okay, you can reuse heritage data for reanalysis, But especially, if I can give you a hint of the next level of discussion, what you're looking at here is somehow the level of the so-called spatial information, which we'll discuss a little bit closer by tomorrow. When you have high spatial resolution, you're collecting more of a type of information which is called spatial information. Okay? So we have spectral information, which is something. We have spectral information, which is described on the key axis. So the spectral behavior will tell us something about what is located in the single pixel. But then there's a part of the story, because the other part of the story is the relationship between that pixel and the surrounding ones. Okay? Imagine, for example, a meadow, a well-mown meadow, homogeneously green, okay? And now imagine spontaneous vegetation, very messy. Both are vegetation. If I use multispectral data, right, what does it look like? Vegetation. Vegetation and vegetation. How can I tell one from the other? Leveraging spatial information. If you have very homogeneous meadow, then you can tell that from messy, natural, spontaneous vegetation where things may change from one pixel to the other. So what is the difference between the two cases? It's not spatial, it's not spectral information, because the spectral information is the same. It's vegetation. It will behave as we have seen this morning. So I cannot leverage that type of information to distinguish them. I need to move on to a different type of information, which is called spatial information. How pixels relate to each other, slightly higher, slightly lower, knee to knee. I analyze one and look at the next one, and I see the differences. Okay, that brings me information, a sort of information which is called spatial information. Okay, tomorrow we'll see something more of this. So this is not south on axis K, it's south on axis I and J. And obviously, the higher the spatial resolution, the smaller the pixel, the more spatial information you're collecting from the scene. And this may be good, or this may not be so good. Because more data means that it will take up more space, but that's not the problem. It's not the only problem. Collecting more information without need means that you're putting noise, you're putting randomness, you're putting information that you don't care about into your problem. Okay? This is a disadvantage. Okay, so generally speaking, what we do in the remote sensing community is, especially if you look at it from information theory perspective, I could say, the idea is you should match the scale, the spatial scale of the phenomenon that you're observing with the spatial scale of the data that you are using. Okay, so this is the reason why spatial resolution is not always pushed to its limit. Because if you push the spatial resolution to its limit, you will for sure collect more information, but this may be information which is not relevant to you and will just complicate your task of getting that information. Does that make sense? From a signal processing perspective, because I'm forced somehow to think of it. From a signal processing perspective, it's just like if you were putting more noise into the signal that you're analyzing, because you're putting variables that don't matter to you, and they will change the numbers you're playing with no benefit to your own application. Okay, so the general guideline here is you should be matching the spatial scale of the problem with the spatial scale of the information that you are collecting. And that's the reason why we have this situation here. And that also applies to spectral resolution. Don't collect more spectral resolution than you need it, otherwise you're complicating your problem. So in many cases, multispectral data works better than hyperspectral because it ignores information which is not relevant to that specific problem. Okay. Yes, sir.
You said that we match generally, it is a trade-off.
Yeah.
Match the size of
Yeah.
interest and from where we are taking.
Yeah.
Or these spectral data are taken from far away.
Yeah.
So we are covering very large area.
Yeah.
If we match the resolution, so we cover large area.
Yes.
So there will be a lot of things may change in single pixel.
Yes, but it depends again. That's why I said you should match the scale of the object or the phenomena with the resolution, because you may have both problems or both sides of the problem. In one case, you may be collecting too much information because you're breaking down the spatial dimension into chunks that are too small. But on the opposite side, you may also be collecting too little information because you decided to use a spatial scale which is larger than the scale of the objects that you're interested in. So for example, if you're interested in detecting individual buildings in an urban area, then you will need a high spatial resolution, because if you use low spatial resolution, all these buildings in the urban area will be blurred. That's also part of matching spatial resolution with the spatial scale of the problem. So if the spatial scale of your problem is a single building, then you will need a spatial resolution which is small compared to the building. But if your goal is that of identifying an urban area, for example, then the very high level of spatial resolution will complicate the problem, because urban areas are typically very inhomogeneous in spectral terms. So if you have small pixels, each one of those small pixels, think of it, will sense very different types of material. Okay, so one pixel may fall on concrete, the other pixel may fall on the pavement, another one will be on the roof or whatever, and maybe even on vegetation. Okay, so if you have smaller enough pixels, then some pixels will fall on urban parks and will be classified as vegetation. So whereas if you use a large spatial scale and you have a large size pixel which may contain all of those different types of different materials and will average them out, you will notice that the average spatial response is much more stable, and it will let you identify the urban pixels with greater confidence. Okay, so that's also an aspect of matching the spatial scale of the problem with the spatial scale of the data. And we're talking about similar problems. We're still talking about urban areas. So we're working in the same environment, but on two different types of problems which require two different levels of spatial resolution. Okay.
I have one more.
Yes, sure.
How generally we don't have any control over sensor.
Yep.
Because we are not getting data from our own sensors. We get data from some different kind of sensors. So in that, how people match this spatial resolution by pre-processing or something like that?
And generally, what happens is you select a source based on your needs. So you're right that given a sensor, you will have certain characteristics for the data generated by that sensor. So you don't have much choice if you focus on one sensor. So if your source is a single system, then generally that's it. But in general, it depends, it's up to you to select the correct source. There are other factors, okay, so including, for example, the cost of data. In some cases, you may make yourself happy with a data source which is not ideal for you. You could have better options from a technical standpoint, but still you go for that data set because it's free instead of the ideal one, which is for a fee. Okay. It's a trade-off between how much you can spend and how well the data set matches your needs. But in an ideal world, the strategy would be, okay, not to design a new system for every application. Sometimes it is done, but it's something which really happens rarely when you really have very good reasons to do that. In the ideal case, you would identify the spatial scale or the spectral scale of your problem, and then you would identify the data source which best matches your needs. Does that make sense? You don't try to tune the system because the system is generally not tunable. It was designed, it was built, it was sent to space, that's it. You may design a tunable system, but it's extremely difficult and expensive. So this is generally not done. Okay. Okay. So now let me see. It's 3:15 p.m. We're more or less at the end of this lecture. Let me just say a couple of words about because we also have radiometric resolution. That was the other point. Radiometric resolution has to do with power. One thing we should remember is that all the systems, all modern systems for Earth observation, for space-based Earth observation, are digital. So they don't generate, their measurement ends up in generating a binary code word, which is then stored in which is then beamed down to the Earth and stored in a computer system. So it's not an analog measurement. It doesn't have infinite precision. So the precision is defined beforehand by design. And generally, okay, I will skip this because it's not of your interest. But the fact is, the higher is the precision with which you define the recorded amount of power, then the better quality the data is. Generally, most multispectral systems use 12, 14, 16 bits per sample to define the measure of power. It doesn't seem to be much, but there are reasons for this. You're measuring a very weak signal. It doesn't make sense to be extremely precise in measuring it because if you are extremely precise, you will be measuring disturbance factors rather than useful signal. Okay, so in this image, I'm just exaggerating the effect of reducing the radiometric resolution in order to show you what the effects would be. And the effects would be that of pressing into a single value a range of values. It may be okay, it may not be okay, depending on the application. But I didn't want to discuss too much this because I think for you it may be more interesting to think of temporal resolution, because we define temporal resolution because in the domain of spaceborne data, spaceborne remote sensing, you use platforms which are located in orbital motion. So since you're dealing with objects in an orbit with a regular pattern, you will have a regular temporal pattern of measurement. The satellite, the same satellite, will fly over the same location times and again. So you will get a regular series of fresh acquisitions every second day, every third day, every week, every whatever. That period is called temporal resolution. You may have different situations depending on how the orbit is designed, but it is important because even in this case, you should match the temporal scale of the phenomenon that you want to observe with the temporal resolution of the system you are using. Even in this case, you don't have much of possibility to act on the single system. You cannot change the orbit of the satellite, but you can change the source of your data. If you're not happy with a certain source, you can move to a different source which will provide you more frequent acquisitions. For example, so if you realize that between one acquisition and the next, too much stuff has been going on, then you may consider moving to a faster revisit time. And this is typically an important factor in agricultural remote sensing, because you want to see this is an example from a student of mine who worked on the topic some time ago. He produced this graphic with the trend of so-called vegetation index, which is an index relating to vegetative activity of the observed vegetation. And you may notice that in Europe, we have a strong seasonality in terms of weather and also as a consequence in terms of vegetative activity. So in winter, vegetation stands still, loses leaves, et cetera, et cetera. So there's very low vegetation activity. Then it improves in spring, and then it reaches the top in early summer. And you can see that in this graph. I don't know if you can read the months here, but we basically have winter here, December, January, February, and then we have full summer here, June, July, August. And you notice that there's sort of a repeating envelope for the curve, higher vegetation activity in summer, lower in winter. Okay, so you can notice that because the acquisition is sufficiently frequent that you can see the change, you can see a smooth change. Actually, if you look at the graph, it doesn't look very smooth. Okay, so you can still tell that there's a sort of sine wave, but actually it's very bumpy. Why is that? No, it's too fast. The seasonal variation is this, okay? But this is definitely too fast. Clouds, yes. Such a sudden, deep and recovery can only be due to clouds. So the object, this is the problem that I mentioned this morning. The problem with multispectral optical is that sometimes, or not just sometimes, but quite frequently, especially in winter, you have to do with clouds. And clouds prevent you from sensible data acquisition. So frequently, when you work with multi-temporal data sets, you have to be able to understand the trend of variations of an index from a very bumpy curve. And obviously, if you increase the temporal frequency of your data set, you're more likely to find a clean acquisition on every portion of the year. Let me show you this, then I promise I will give you a break. This is a lake next to a city in northern Italy, not very far from us. You see the same seasonal variation: winter, summer, winter, winter, summer, winter, except you're looking at a water body. Interestingly, you look at a water body, and from time to time, actually in summer, you find that the vegetation index suddenly goes up and it remains there for the entire summer, and then it goes back to 0, which is the expected value for water. What do you think may have happened there? There's a hint there, but it's written in Italian. So. Sorry? No, it's not moisture. Because moisture is consistent across the year. It's not seasonal. It's lotus flower. It's actually vegetation. In summer, in that lake, in winter it's too cold, but in summer, there's this phenomenon for which the heat makes lotus plant leaves to appear on the surface of water. And the time series of satellite data has captured the emergence of this vegetation unexpectedly. Let's see.
It is every day data, right?
Every
day data.
No, this is every 3 days.
Every 3 days?
Every 3 days. It's Sentinel-2, so it's every 3 days. It may be even less, maybe 5 days, depending on the location. But if I remember correctly, this is every 3 days. Okay. Yeah, okay, no, I think this is all for this first part of the afternoon. So now we have a short break. And then I understand we are expected in a lab. So the next lecture for the second part of the afternoon is not going to take place here, but in a different room, right? Okay, so we are moving there. So thank you for being here. I know in the afternoon is even worse than in the morning. I mean, in the morning, people are generally more awake and more willing to withstand a person who keeps speaking and speaking and speaking, whereas in the afternoon it may be a little bit more difficult. But I congratulate with you because you seem to have been attentive even in the afternoon more than expected. So thank you. I appreciate it.